Okay, so I'm grateful to the Turing Institute for this opportunity to say a bit about what I'm interested in data analysis. And thank you to the audience for coming along. My roots, or the roots of my interest in data analysis, go back to this Ratio Club. Ratio Club is a group of people who got together less than a mile away from here to talk about cybernetics, which is the science of control and communication in the animal and machine. These days we would call it artificial intelligence, and it's a basic ingredient of what the Turing Institute is doing. And you may have seen this morning the UK government is dead keen on it and announced a $1 billion deal in artificial intelligence. So in this picture, you will see Alan Turing himself, who is part of the club, and also my father, Donald MacKay. So I served as data source to him when I was a young child. I remember spending several Saturday mornings having electrodes stuck in my head while he would analyze what was coming out of the electrodes and make me look at flashing lights in order to work out how the visual system was processing information. I'll talk about 4 topics and which I've been working in. First one is topological data analysis. Many people would say this started with the paper of Brunell et al. In 2002, but we were already doing it 10 years before. So this is evidenced by this paper, Topology from Time series, published in 1993. So why were we into topological data analysis? Well, Floris Takens proposed that the attractor in a fluid mechanics experiment run by Harry Swinney in Texas was a twisted 3 torus, meaning a certain non-trivial circle bundle over 2 torus. Dave Brumhead asked me how we might test this hypothesis. And I said, well, let's make a simplicial complex from the data and compute its Betti numbers. A twisted 3 torus will give Betti numbers 1, 0, 0, 1, whereas a standard one will give 1, 3, 3, 1. And we had a joint postdoc at the time, Mark Muldoon, who's now at University of Manchester, and he coded it up, and actually everything I'm going to say on this topic is really due to him. He took on this project completely and with fantastic results. Well, what are the results? Firstly, there was a bit of a problem. Swinney said he couldn't find his data, and he couldn't rerun the experiment because it had all been dismantled. Furthermore, Takens said that actually his interpretation of a twisted 3 torus was wrong because it was incompatible with something else. So our interesting problem somehow went away. But Tom Mullen from Manchester University provided us with data from a convecting liquid gallium cell that he'd set up. And we applied Muldoon's program to this. Here is a sample from the data. This is only 50 seconds worth, but he gave us 100 minutes. And the program produced Betti numbers 1, 2, 1, which is what you'd get for a standard 2 torus. And indeed, anyone looking at this would say, well, it looks 2-frequency quasi-periodic. So this is good confirmation that his method was working. And the way we did things is to choose, in this case, 121 data points out of a huge sample. These days, they'd be called witness points. And so there are nodes, if you like. And then we put edges. We put an edge between 2 of these nodes if there exists a data point which is within some epsilon of both of them. And we put a triangle if there's a data point which is within epsilon of 3 points, etc. And then you can compute the boundary operator, which Muldoon coded it up, and work out cycles modular boundaries, and you get these homology groups. So for those of you who know the Brunell et al. Paper, its main achievement was to create the concept of persistent homology. So did we invent it? Well, no. but we had all the ingredients. The point of persistent homology is to find scales, this epsilon I was talking about, where the homology doesn't change. And of course, that's exactly what we did. We searched around for a scale where it didn't change. And we had the ingredients that go into the construction of persistent homology, which maybe I won't read out. But so we were there, but I just didn't make it explicit. Lots of people have played around with topological data analysis subsequently, but I'd still like to see an application that's as good as our initial goal, deciding if we had a twisted 3-torus or a standard 3-torus. Okay, next topic is panel assessments. In 2001, I served on the research assessment exercise panel for applied maths, and we had to, between the 12 of us, assess 3,600 papers. And the chair assigned each paper to 2 assessors. But the obvious question came up: how do we deal with the fact that different panel members may use the scale in different ways? And the second fact, that different panel members may express different levels of confidence in their assessments. There's also a further question: how do you do inter-panel comparisons? So when I was asked to serve in RE 2008, I decided we'd better tackle this head on, so I devised a method. And the method is rather simple-minded. We fit the scores that the assessors give, so SAO for assessor A on object O, to a relationship of the form a true value for the object O, a bias for the assessor, and an uncertainty times a random variable. This method, unfortunately, wasn't adopted, but eventually I got it coded up, first by a student, Sarah Parker, and then Rob Lowe and Ralph Kennett made their versions in Coventry University. And then Marcus and Dan here from Spectral Analytics coded it up in Excel and Python and GUI, which you can download from this website. And we wrote up the paper. And I just want to give a quick demo of this. So here, I'm afraid it's rather, maybe it's too small to see what's going on, but we have an Excel file which has fictitious students, Albert, Becky, Charlie, so on, and they're assessed by Lockhart, McGonagall, Quirrell, Pomfrey, etc. That names you will recognize from Harry Potter. And each of these assessors gives a score for each of the things they assess, plus an uncertainty. And the calibration method will produce true values for the objects, plus an overall uncertainty measure. So if we click here, and we have to make sure I'm using standard deviations, and I want the weighted degeneracy breaking, and I'll say OK. And there it's produced the results. So here we have notional true values, and here we have a confidence-weighted root mean square error, 5.1 something. To me, this is quite interesting because it shows that one shouldn't put great reliance on differences less than 5% in these marks. And if we want to achieve a more reliable, accurate assessment, then we have to do more assessment. Have more assessors for each object, or get the assessors to really refine their uncertainties as small as possible. And we got interest from Times Higher Education in this, but we haven't yet managed to get it into the ref, despite my writing to Nicholas Stern about it. But I'll see him tonight, so maybe I'll get a chance. Third one, detection of oscillations in power flow. This is a problem that was posed to us by National Grid in 2015. They asked if we could improve their methods for detection of oscillations in power flow, in particular estimating the frequency of the oscillations, the damping constant, and the mode shape. This is an example. Time is horizontally in seconds, and here are phase differences between the voltage measured at different points. So these label the different points relative to 1. So this horizontal line is the one they're all taken relative to. So you can see here that some oscillations have started up, and phase differences drive power flow. So this basically corresponds to oscillations in power flow. Of course, this doesn't really need a fancy method to detect, but the question is, can we see nascent oscillations in the normal behavior here? And that's what National Grid wanted, because they have to design control methods to cope with potential oscillations before they happen. And this picture is taken from a paper by Phil Ashton, was one of the people we talked to in National Grid. So I said I'd give it a try, and I started down one track, but then asked my brother what he'd recommend, and he said, use the Gaussian process. It was a really short email, that was basically all it said. So I thought, well, I'll read up about Gaussian processes, and let's see. And I read up and thought, yeah, actually this looks a good idea. So here's what I did. Made a model where phase differences and frequencies are forced by power imbalance noise, difference between supply and demand. And I modeled the power imbalance noise by filtering white noise, which may or may not be accurate, but it seemed to me a starting point. So then the point is to fit a Gaussian process corresponding to the most significant modes of such a linear model. Well, let's start just with simple-minded things that only have two dimensions. Linear Langevin equation, mx double dot plus a damping times x dot plus a restoring force kx is some amplitude squared times a white noise. And here are two samples that I got the computer to produce. In the so-called underdamped regime, that's when the eigenvalues are complex. And you see we're getting things that oscillate up and down in an irregular way. And what's surprising to me is that in the Gaussian process literature, it seems that the corresponding covariance function is hardly used. So this seemed to me a very natural class of Gaussian processes to start from. Here is in the overdamped regime, when the eigenvalues are real and negative. Here's a sample, and here for comparison is a trace of frequency at one location, which was made publicly available by National Grid. And, well, you know, it looks the same sort of thing. And indeed, I got GPML, a Gaussian process for MATLAB, to infer best fit parameters by such an overdamped linear Langevin. I don't know how meaningful they are, but it looks like it's a reasonable fit to the normal behavior. But I wanted to extend a bit because one can consider the general stable 2D linear autonomous stochastic system. And the covariance of one component has this form: an amplitude, a decaying exponential, and a cosh of something plus some coefficient j here times a sinh. And the parameters correspond to the matrix for the 2D linear system. So mu is a half trace. Beta is square root of something that may be positive or negative, corresponding to the overdamped or underdamped. And j is limited to the range 0 to -1 to +1. And I've written it this way. Of course, if delta happened to be negative, then beta would be pure imaginary. Then the cosh turns into a cos, and this sinh turns into mod t times the sinc function. And fortunately, things like MATLAB can cope with that automatically without one having to code up. So it's convenient to write this thing beta in the form of mu. We take out the time scale mu times square root of 1 minus e to the s. So the point of this is e to the s is positive, and that actually enforces the stability condition. And s equals 0 separates the overdamped from the underdamped case. So what we have is a 4-parameter family of Gaussian processes here, with amplitude, a time constant, and then a frequency, or in the case this is imaginary, or another time constant, and a j which actually governs smoothness or not. So I coded this up in MATLAB, And I'll show you that if I can find the right one. Yep. Yeah, that's the right one. So here is a sample in the underdamped regime, and I can change the sign of one of that thing S basically, and give you a sample in the underdamped, the overdamped regime. Sorry. And we can change the smoothness parameter, which I'd set to be perfectly smooth here, but let's change it to make something non-smooth. And there you can play around. And the other two parameters are just an amplitude and the time scale, so they don't really do anything. So this seems to me like a really useful family of covariance functions that ought to be used very widely. So in doing this work, I happened to go to a talk by Magnus Rattray from Manchester, and he presented one of the cases of this family, so with J as 0, in fact, and said that he was using it in gene oscillation detection. And so I've corresponded with the postdoc, who was Nick Phillips, who's worked on that. And Nick said, actually, he's been developing these 4-parameter family things as well. So we should join forces on that. And I'm pleased that Manchester has joined as a formal partner in the Turing Institute, and actually Magnus Rattray is the Manchester leader. Right, so back here. So what is the way forward? What I've told you about is far too simple in order to do what National Grid wanted, because it only had 2 dimensions. But the way forward is to make a multi-channel version of this and allow multiple modes. So on paper, I know how to do this, but the question is coding it up and seeing whether it's actually usable and interesting and useful. Another step that I really want to work on is to do the inference in streaming mode. So I was just doing batch mode in what I was doing here. But in principle, what National Grid wants is something that's on the controller's desk and will flash up when something's going wrong in real time. So we really want to implement this in streaming mode. So I'd be very grateful for anyone who has experience of that sort of thing. Unfortunately, National Grid terminated the contract. So I haven't got on very fast with this, but I still think it's a good idea, and I'd be pleased to collaborate on it. So the last topic I'd like to do is some version of the same thing, actually, which is value tracking in financial markets. So this is a topic that I've been collaborating with Nicholas Beale and his group, and I'm pleased to see some of you in the room here from that collaboration today. And currently we're looking at the extent to which financial markets track or don't track value. Now, a big philosophical problem with this is that does value have any objective meaning? It could just be in the eye of the beholder. But our idea is that we should make models that do have some variable called value, and then see if we can infer this value from data. And if we manage to infer something reasonably precisely, then maybe that value has meaning. So I propose to infer value via a Gaussian process. Of course, people will tell you financial data is not Gaussian. Even log price is not Gaussian, but I'm doing it for the moment. So this model says that price, actually log price, rate of change, is determined by the rate of change of log value plus some momentum variable, and there's a mean reversion of the price to the value plus a noise. And momentum is determined by a mean reversion of the momentum to the average rate of change of the log price, but forced by a noise. This is basically was stimulated by a Gaussian process by Bouchot et al. But I've adapted it to allow for non-trivial value functions of time. So the idea is the value function of time should be some external thing that we want to infer. And it should have the features that it's slowly varying most of the time, except it should be allowed to have jumps when there's some news, if a company publishes results, or there's some disaster, or some great breakthrough. So this is the model. And here is an example where I just said, well, let's look for a value function that's an affine function of time, at plus b. And what it's done is to find, I generated a sample from a model that did have an affine function of time for the value, log value, and it's found the best fit with this slope. It was generated with one with a smaller slope, actually. But I only observed at these plus points in the middle to do the inference. And more interesting, which I'll just demonstrate to you, is to look at data that has potential steps in it and to infer steps. So if I go to my MATLAB again and run a different one, and let's expand that so you can see it. So I generated a sample. This sample was generated by assuming that value was a two-step function, this blue curve. And I got the inference to fit a one-step function, just to see what would happen. And, well, it found the biggest step. That's not bad and could be useful. So this is one of the directions that we're pursuing in our collaboration. Of course, if it really works, we'd better stop talking about it and make loads of money from it. Good. So back to here. So in conclusion, I've addressed 4 topics that I've been working on or am working in: topological data analysis, panel assessments, detection of oscillations, and inferring value from financial markets. And I have one question. I wonder what Turing would have thought about these problems, and also about the current interest in artificial intelligence. And I'd like to thank you for your attention and invite your questions.